Hello and welcome to this lecture. So this lecture is going to be all about continuous random variables, in particular something called the probability density function. Okay, so for the discrete random variable, we had the probability mass function, probability that the discrete random variable takes a particular value and all that. When you come to the continuous case, it seems a bit odd that you can't have the PMF anymore. PMF doesn't give, it gives you just 0, 0, 0, 0. It doesn't make sense. Okay, so you need something called the density. Okay, so the continuous random variables will take values over an interval. They'll have a certain density over that interval, but not over a particular value. So it's sort of continuum in that case. Okay, and there are a lot of continuous distributions, very interesting distributions, defined by different density functions. So this density function plays a very, very crucial role, makes calculations very easy for continuous random variables. I mean, I'm saying very easy, but it's a little bit more involved than discrete. But it's density function, sort of like the analog of the PMF in the continuous case. Okay, so we'll see why that is true. So you might wonder, I mean, already we saw the CDF, why not use the CDF for everything? It turns out the CDF is not that easy to deal with when you want to do calculations. Okay, so the density, on the other hand, is a much more intuitive and natural thing to use. Okay, a quick refresher on integration. I think you've probably learnt integration in the Math 2 course if you're doing it along with this, or you've done it before, or you have already some background on integration. It's just a quick refresher so that we are on the same page. Okay. Usually one talks, first of all, before you come to integration, you have to be comfortable with differentiation. This is derivative of a function which represents the slope of the function at a particular point, or its rate of change when you focus on a very small region around a particular point. How fast it's increasing or decreasing is captured by the derivative, and there are formulae for derivative. Okay, given a function, given a description of that function, what is its derivative? There are tables which tell you how to do this, etc., etc. Okay. Now, if you have a function small f, okay, and there is a capital F whose derivative is small f. Okay, so notice the inversion here. Okay, so usually given a function, you differentiate, you get the answer, right? Now here we're doing the reverse. Okay, you have a function small f, which function when differentiated will give you small f. Okay, so that is sort of called the indefinite integral of that function. Okay, so roughly something like that. It's, of course, I'm being very imprecise and loose here just to get you a rough idea of what it is. Okay, so people usually write integral f of x dx for this, and they'll write capital F of x like that. So it's also called the antiderivative or something like that. Okay, so capital F of x and small f of x are related in that fashion. Now, once you have an antiderivative, you can do something called a definite integral for your small f. Okay, so this notation, integral from a to b f of x dx, is capital F of b minus capital F of a. Okay, so this definite integral is density under the curve. So a very usual picture, very common picture, is supposing you have a function f of x. This is a function f of x, and you go from a to b. This area, okay, this area is given by this guy. Okay, so integral a to b f of x dx. This is just notation for that area, and that's given by f of b minus f of a. Okay, so how do you find the antiderivative? There are these tables of integrals. You can go and look it up. This is not the only table out there. There are so many other tables. So given a f of x of a certain form, you usually know what the antiderivative is. Okay, and today many computer packages can calculate the antiderivative, the definite integral for you. At least numerically, to whatever extent it's possible, you can calculate the definite integral. Okay, so it's just a one-page refresher, so that we are clear on notation, and we will use this notation a lot. You can see now already the capital F of b minus f of a, that's like the CDF. So the small f is something inside. When you integrate, you get the CDF. So you can see where we are going with this, and where the density comes sort of naturally. Okay, so this is a quick refresher on integration. Okay, so now this leads us to the definition of what's called the probability density function. Okay, if you have a continuous random variable x, remember what's continuous random variable? Random variable whose CDF is continuous at every point, right? So that's the continuous random variable. It is said to have a probability density function, which is usually denoted small f. Okay, the CDF is denoted with capital F, probability density is denoted with small f. Okay, if for every x naught, okay, the CDF evaluated at x naught should be the integral from minus infinity to x naught of the PDF. Okay, so this is the idea. So if you want, I can draw a picture here. Okay, so this picture became very ugly. We draw a picture here for you. Okay, so let's say you have a CDF here. Maybe I should draw the PDF. So you have a function which is like this. Let's say this is fx of x. Okay, so now so let's say this is x naught. Okay, what is integral from minus infinity? So minus infinity is something way out there. Okay, so integral from minus infinity to x naught of fx of x is what? It's the area under this curve all the way here. This guy has to be equal to capital Fx of x naught. Okay, so this is what's happening. So this right hand side is actually representing this integral. So if x naught moves, the integral will keep changing. The value of the definite integral, the area under the curve that you're including will keep changing. So you can see as x naught increases, the area under the curve only increases, right? So it's a non-decreasing function, it's an increasing function. Okay, and this fx of x naught has to be between 0 and 1, it has to be a probability, it has to start at 0, end at 1. So that puts some conditions on the density, but this is the meaning of the density. Okay, if you can express the CDF as the integral, as the indefinite integral from minus infinity to x naught of some other function, then that function becomes the PDF of the probability density function of your continuous random variable. Okay, so CDF is the integral of the PDF. Now what do I know from my basics of integration? So the derivative of the CDF is going to be the PDF, right? So how do I get, see when I do the integral, the indefinite integral is going to be what, right? So notice, so this is important. The derivative of the CDF is the PDF. So if you want to integrate, so if you have the PDF fx of x, its antiderivative is capital Fx of x, isn't it? Right? Derivative of the CDF is usually the PDF. So it's directly taken as the PDF. Okay. So when you differentiate this with respect to x, you're going to get the PDF. Okay. The antiderivative is this. So when you do integral from minus infinity to x naught fx of x, what will happen from your relationship of definite integral? It's going to be fx of x naught minus fx of minus infinity. What's fx of minus infinity? This is 0. So you get your you get what you want, right? Okay. So this is what you will get. Okay. So if you can, so this is the standard way of getting the PDF. Okay. The definition is sort of like done in ulta fashion, but you have a CDF. The CDF is given to you. You simply differentiate it. Wherever you have the derivative, take that as your PDF. Okay. So in most cases, you will have a derivative, and you just have to use the table, differentiate the CDF. You will get your PDF. Okay, so for just to be technically correct, I'm defining it in this fashion, but usually you just take the CDF, differentiate it, you get your PDF. Okay, derivative of the CDF is the PDF. It's a very good rule to remember. Okay, so that's correct. Okay, so why PDF? People might ask. I have a CDF. I'm already confused. I'm computing probabilities. Why do you want to confuse me more? Well, that's one of the reasons why we have all these definitions, isn't it? We can keep asking you more and more complicated questions, confuse you about it. No, that's not the reason. A PDF is really useful. What happens is, whenever you want to have a measure of some distribution, right? So you have a distribution of the values, and you're describing it with the CDF. Whatever function you used to describe, if that function is high, you want the probability of x taking a value there to be high, right? Or if it is low, then probability is low. Notice what happens in the CDF. It keeps on increasing, right? And just because the CDF is higher, it really doesn't mean that x takes more values there, right? Only the difference matters, okay? It's only between 0 and 1. It's a different sort of definition. On the other hand, the density is not like that. The way the density behaves, you'll see soon enough. If the density is higher, then x takes more values around those points. Okay, so I'll give you very clear calculations to show you how that is true. So the density is sort of like a truer. I mean, if you see the density, you sort of see the distribution. Okay, if you see the CDF, you're not quite seeing the distribution. You're seeing how the probability increases and all that. Maybe some of you can visualize, but it's not so easy. On the other hand, the density, you will see it's very, very easy to visualize. I'll show you some plots. You'll see it makes a lot of sense. Okay. So for instance, the CDF will go and saturate at 1. Okay. So it's probably the highest value of the CDF. But once it is saturated, it never takes a value there. Okay. X will never lie there, right? So it is confusing to deal with the CDF for that reason. You would want the function, some function that represents the distribution. If X is never going to take a value there, it should be 0 there, right? The PDF will satisfy that. Because if it's flat, if you differentiate, you're going to get 0, right? So that's why the PDF is much more intuitive and easy to deal with, and many complex calculations, believe me when I tell you, PDF is so much easier to deal with than CDF. Okay, so that's why PDF is used in many computations. Okay, so it's not just to confuse you, except for this integration and differentiation. You need to be able to differentiate, and some integration is involved when you calculate probabilities with PDF. That is not there in CDF, but it's okay. You can get used to that, and PDF is very, very useful. Yes, examples. Okay, so examples are always good. The first, these are all uniform distributions, by the way. Later on, we'll see what it is. Look at CDF 1. It starts at 0, and then just flat line increases to 1 at 5, and then it's flat again. Okay, so CDF is like that. But notice what the PDF is. Okay, I have to take differentiation, right? So if you differentiate a constant, a flat thing, when you differentiate, you get 0. And then this equation is actually, so supposing you call this fx of x, and this is x, this is actually x by 5, isn't it? At 5, it hits 1, at 0, it is 0. So this is x by 5, okay? And this is 1, and this is 0. So when you do derivative, 0 is flat, so it keeps on being 0. X by 5, the derivative is 1 by 5, okay? Oops. So this is fx of x versus x. Okay. So x by 5, the derivative is 1 by 5. And notice what happens after 5, it goes down to 0 again. Okay, why? It's 1 flat, and then constant is differentiation is 0, right? There's no slope here. The slope is flat. Okay. So notice how intuitive it is, like the PDF, right? The random variable takes values only between 0 and 5. The PDF is non-zero only in 0 and 5. It is 0 outside. So the PDF goes to 0, you know, the random variable does not take values there. Okay, so it's a very nice property, simple property the PDF has. Looking at the PDF, I can say that. Okay, and it's 1 by 5. So I know how the probability will work out. So we know how to do probability calculations with CDF. You can also do probability calculations with PDF. We'll look at examples later. You have to do integration. It's a little bit different, but you can do that also. We'll see enough examples later. Okay. So here is another CDF. So here in this case, what happened is, so this point is 0.5 or half. So this equation is 2x. Okay. So this is 0 and this is 1, and this again is fx of x versus x. And if you look at small fx of x versus x, for the flat, it is going to be flat at 0. It's flat at 1, it's going to be flat at 0. When you take derivative, you get 0. And then for 2x, what is the derivative of 2x? If you go look at your formula, you'll say the slope is 2, so derivative is just 2, so the PDF goes to 2. Okay, so it is 0, 2, and then 0 again. Okay, so let's contrast these two pictures. Okay, so the distribution on the left, the random variable takes values between 0 and 5, sort of uniformly. The PDF is flat, the density is flat, so we say it's uniform. Okay. In the right hand side picture, the random variable takes value only between 0 and half. It's sort of concentrated, so the density is higher. Okay, so when the random variable takes a smaller range of values, the density is higher. One point where everybody gets confused is the density can go above 1. Okay, so this is a probability we are dealing with. Probability density, it's not probability itself, right? So probability density can go above 1 also. The CDF will never go above 1, right? The CDF is always between 0 and 1. The PDF, on the other hand, can go above 1. It's sort of like density. Density is what? Amount of probability per unit length. Okay, so that's the way you have to think of density. That's why it's called density, right? Density is what? Weight per volume or something like that is density, right? So likewise here, probability per unit length is your density. So it can go up to 2. Okay, so when density goes to 2, your length cannot be great, right? Your length goes only up to half, right? So 2 into half is 1, so you're still within the probability regime. Okay, so density can go high if the range shortens up for you. Okay, so this is a good picture to remember. So notice how, once again, I would say the PDF is so much more intuitive. Just when you look at it, you know where the values are, right? So wherever the PDF is high, the values are going to be there, right? If it's flat, then it's equally likely, sort of uniform all over that place. Okay, otherwise it can take differing values. Okay, so that's a good picture of simple CDF PDF illustration. The derivative is very easy and all that. Okay, let's complicate things a little bit more. Here are two other distributions. These are called exponential, normal. We'll come back and look at exact formulae for this, but I just want to point out that in every case, when the CDF is smooth also, the PDF ends up being smooth. It has a nice behavior, and always wherever the PDF is high is where the values of the random variable will be. Okay, so look at the top, the left picture here, top left and bottom left. From the top left, maybe it's difficult to figure out. I mean, people who know enough about functions will know that this function is growing faster near 0 and it is slowing down its growth as it goes up to 1. It's difficult to see, but look at the density. The density immediately tells you the picture, right? So it's high around 0 and it tapers off and falls very sharply as it goes higher. So you know that this random variable tends to take values between 0 and 2 most of the time. It's going to go about 2 and all probability is going to be lesser. Okay, so the density indicates where the random variable's probability per unit length, where it's very high and all that. Okay, so that's the sort of picture you should keep in mind. The right distribution is a very, very famous distribution. You would have thought about the bell curve, so to speak, right? So this is an example of that normal distribution. We'll see later on what the formulae are. Once again, I will argue that the CDF probably doesn't quite tell you immediately where the random variable is going to lie, but look at the PDF. It just immediately brings out that most of the time the values may be around 0, and then it can take other values, and it's sort of symmetric, right, around 0. So it can take positive, negative values equally, but look at the PDF on the left side, like it's only going to be positive, it's never going to be negative. Okay, so all these nice quick things you can come up with the PDF, and it's very, very useful as well for doing calculations. Okay, so hopefully you're convinced that the PDF is a good thing. Okay, so it is a very good thing, as we will see soon enough. Okay, so what are the properties? How do you identify a PDF? What are the properties that the PDF has to satisfy? Okay. So here's the definition of a density function. You remember we had a definition for a distribution function, right? Cumulative distribution function. Which functions are valid CDFs? Like that, which functions are valid PDFs? What functions are valid densities? Okay, here are the three properties. Okay, the function has to be non-negative. It has to be greater than or equal to 0. Why is that? It's the derivative of an increasing function, right? It has to be non-negative, so that's how it will be. Okay, and anyway, it's a probability density. You cannot go negative. Okay, so if you go negative somewhere over an interval, probability cannot go negative. It has to be positive, so it will be positive. If you integrate from -infinity to infinity, you should get 1. Okay, so that's not very difficult to see. Why? Because integral from -infinity to infinity of f of x, if you write it in terms of the CDF, it becomes f of infinity minus f of minus infinity. That's 1 minus 0, that's 1, right? So that's one thing, one way to think about it. The other way to think about it is the total probability has to be 1, right? You integrate out all possible values that x can take, you should get 1. Okay, and f of x has to be what's called piecewise continuous. It's sort of like a technical property. It cannot, it has to, if in every interval, sort of, it has to be continuous. Okay, so it cannot do, it can have jumps, right? PDF can have jumps. It's not that it doesn't have to have jumps, but every piece of it has to be continuous. Okay, that's all. Okay, here are more important properties. In fact, the last property is probably the most important, and let's come to that. Okay, the first thing is about existence. If you come up with the density function, so you remember, if you come up with the CDF, I told you that there is a random variable with that CDF. Same thing is true for density. Okay, if you come up with the density function, there is a continuous random variable whose density is that function. Okay, so you can so cooking up a continuous random variable is like cooking up a density function. You come up with any density function that satisfies this, non-negative, integrates to 1, piecewise continuous, you have a continuous random variable. Okay, Now, there is something called the support of a random variable, a continuous random variable particularly. The support is basically the points at which the density is strictly greater than 0. Okay. So, those are the possible intervals where x can take values. Remember, this is a continuous random variable. I cannot say x equal to a particular value with non-zero probability, but intervals where it falls, the PDF has to be strictly positive. So, places where strictly positive is called support of the random variable. I will use this support over and over again. You will see, for instance, so this minus infinity to infinity looks very ugly, but I can write like this: support of x, fx of x will be equal to 1. So, this is a definite integral over the support of x, wherever fx of x is non-zero. If it is 0, of course, it does not contribute to the integral. So that is an easy thing to say. I have this habit of dropping things like dx and all that, but it's just extra fitting in some sense. But anyway, it's good to write it down. Integral over the support fx of x dx is equal to 1. Okay. Now, come to the last point. I put it as the last point. It's that's the most crucial point. Okay. If you have an event A defined using the random variable, how do you define events with a random variable? You say x is less than or equal to something, x is greater than something, x is between something, x is between this or x is between that. Okay, things like that. How do you find probabilities of those events using the PDF? We know what to do for CDF. What do you do for PDF? You simply integrate the PDF over those intervals. Find the area under the curve over the intervals that you are interested in, and that gives you the probability of that particular event. Okay, so this is how we use the PDF directly to calculate probabilities. Okay, so this last property is very important. We'll see a few examples that will be clear to you. Oh, there you go. Immediately we jump into examples. I believe there is 2 or 3 examples before we jump into common distributions. I'll just do the 3 examples and we'll stop this lecture at that point. Okay, so here is the function for you. Okay, this function is 3 times x squared between 0 and 1, and it is 0 otherwise. Okay, so first thing is you have to show f is a valid density function. So what are the valid density function conditions? F of x is greater than or equal to 0. That is true. Okay, integral minus infinity to infinity, but it's just 0 to 1. 3x squared dx. Okay, what is the antiderivative of this? What when differentiated will give you 3x squared? X cubed, isn't it? So it's x cubed, right? Evaluated at 0 and 1, right? So this is how people write it. X cube you evaluate at 1 minus x cube at 0, so that's 1. Okay, and is it piecewise continuous? Yeah, it is piecewise continuous. It's usually an easy thing to check. So it's a valid density function, no problem. So let's consider a random variable x with this density. Okay, what's the probability that x equals 1 by 5? Okay, so this is the easiest thing to answer, right? So any random variable which has a PDF or defined using the PDF is definitely a continuous random variable, and once you have a continuous random variable, probability that it takes equal to 1 by 5 is actually 0. What's the probability it takes 2 by 5? Again 0. Okay, so all easy questions. Now what is the next thing? This question is a bit interesting. So what's the probability? So maybe we should sketch this f of x, right? So let's sketch this. It looks like this. Oops, what did I do? It looks like this. From 0 to 1, it's 3x squared. At 1, it becomes 3. Okay, and 3x squared will go something like this. Oops, what happened? It will go something like this. Okay, it's a curve. It will be like a parabola. It will go like this. This is your f of x. Okay. Now 1 by 5 is somewhere here. 2 by 5 is somewhere here. Okay, so at 1 by 5 and 2 by 5, so if you look at f of 1 by 5, it's 3 times 3 by 25. F of 2 by 5 is 3 times 4, it's 12 by 25. Okay, so the density at 2 by 5 is 4 times the density at 1 by 5. Okay, so what I'm doing here is asking for the probability that x lies within 1 by 5 minus epsilon and 1 by 5 plus epsilon. Think of epsilon as something small. Okay. Notice the density at 1 by 5 is around 3 by 25, at 2 by 5 is around 12 by 25. But to compute this probability, what do I need to do? I have to integrate 3x squared, okay. So, remember that I have to integrate between 1 by 5 minus epsilon and 1 by 5 plus epsilon my density, okay, and that is x cubed evaluated between 1 by 5 minus epsilon 1 by 5 plus epsilon, okay, and that if you do this you will get 1 by 5 plus epsilon whole cubed minus 1 by 5 minus epsilon the whole cubed. You can do this calculation, you will get what? I don't know. So, I hope I'm right here, 6 by 25 epsilon, and then I would get plus 2 epsilon cubed. Okay, so this is the, I think it's the correct answer. So, you get 6 by 25 times epsilon plus 2 epsilon cubes. Let me just make sure I get that right. 3 by 25 epsilon minus 3 by 25 epsilon. The other one get cancelled. And this, yeah, I think this is correct. So, you get this value. So, you see if you think of epsilon as something very, very small, this guy is probably much, much smaller than epsilon. So, you can sort of ignore this term. It's going to be, think of 0.01, right. So, if epsilon is 0.01, this term is of the order of 0.01 something. This one is 0.01 part 3, okay. So, it's going 0.000001. So, it's becomes very small, okay. So, this guy maybe you can sort of not worry about. So, this is roughly about 6 by 25 epsilon. The probability that x lies within a small interval of 1 by 5 is 6 by 25 times epsilon. So, notice at 2 by 5 the density is higher, okay. At 2 by 5 density is higher than at 1 by 5. So, the probability that x lies within that same 2 epsilon interval around 2 by 5 better be a little bit higher, right. So, is it higher? Let us check that. So, probability that 2 by 5 minus epsilon less than x less than 1 by 5 plus, sorry, 2 by 5 plus epsilon. It's going to be integral, the same thing again. So, let me cut that short. It's going to be 2 by 5 plus epsilon whole cube minus 1 by 5 minus epsilon the whole cube. So, that's going to be 6 times, oh sorry, this is 2 by 5. 6 times 4, that's 24 by 25 epsilon plus 2 epsilon cubed. Once again, maybe this one is much, much smaller than epsilon for small values of epsilon. And you can see that this is 4 times, okay, and good enough. I mean, we saw that the PDF itself is 4 times around 2 by 5. So, now this epsilon you have to be slightly careful about. I mean, this is not exactly like at 2 by 5, at 1 by 5, 4 times, yes, sort of like that. But to get that exact probability, you will have to account for the every possible value that comes, okay. I mean, to get the exact probability, you will have to do indefinite integral, find the derivative, antiderivative, substitute the values and subtract and all that, okay. But I want to bring out this point that this PDF actually represents the probability that x takes values around that point, and when the PDF is higher, it is true that x takes values around that point with a higher probability than a comparatively lower point, okay. But this kind of trick is very important, this skill is very important. Given a particular function, identify whether it is a valid PDF or not, and then compute probabilities for events involving that random variable as integration. This integration will come in and you should be comfortable with that. We'll use simple functions mostly in this course, and even otherwise in practice there's no need to be worried about integration. In practice you always have tables and Wikipedia to help you and all that, so you can find integration without too much of a problem. Okay, so here's another problem, something very, very similar, just for you to get comfortable. This is 2x. So once again, if you like sketches, you can sketch it. So this is the density, remember, 0 to 1, it goes up to 2. It stays, sorry, it doesn't stay there. Remember, this density, it can't stay there. It comes down to 0. So this is how the density is. And this is, you can calculate the area under this curve. It's half into base into height. So that's 1, right? So it's a valid density, okay? So what's the probability that x is between 0.1 and 0.3? So remember 0.1 and 0.3 somewhere here, the densities are like that. So how do you do this? So this probability that x is between, this is, it's s less than or equal to, it doesn't really matter, 0.1 to 0.3 of 2x dx. The antiderivative is x squared, okay, x squared between 0.3 and 0.1, 0.09 minus 0.01, 0.08, right? Okay. So you can calculate the others, all of them in the same way. You know, I'm just confusing you with, you know, open here, closed here, open there, closed there, etc. You'll get the same answer. So just for comparison, supposing you look at, see, this is an interval of length 0.2, right? So let's say we look at the same 0.8 and 1. Okay, so same interval but situated at 0.1. So this you will get as, you know, 1 squared minus 0.8 squared. So that is 0.36. So notice how much higher this probability is compared to that probability. Okay, so that would work out in that fashion. So I'll leave the remaining things as exercise for you. So being able to integrate, calculate the difference of, you know, the antiderivative, substitute, etc. That's very, very important. You can also find the CDF, right? So the CDF you can see. So what will be the CDF here? The CDF, if you do the CDF, it will start at 0 and go at 1, and then it will be x squared. Okay, so this is 2, and then it will, no, sorry, it will be 1. Okay, but it will be x squared. Okay, so this function will be x squared and start at 0 and end at 1. At 1, it will go flat. Okay, so this is how it will be. So notice how the CDF and the PDF, you know, this is the antiderivative becomes the CDF, and notice how the CDF doesn't truly tell you, you know, how the probability is going to behave, and the PDF is telling you exactly how the probability behaves. So let me close with another simple type of problem. This is again a very typical problem. Given a function like this, there is this parameter k which is not specified in the problem, and you have to find a k to make it a valid density function. First thing you check is k has to be non-negative, and it lies between 0 and 1 by 4k, it's 2 by 2k, 3k, etc. So if you want, you can sketch it. 0, 1 by 4, 3 by 4, and 1. It goes to k here, and then 2k here, and then 3k here, right? So this is the function. Okay, so here the only thing to use is that the entire PDF, the area under the curve, the entire integral has to be 1. So if you look at the integral 0 to 1 in this case, right? So takes the value there, f of x dx has to be equal to 1. So now 0 to 1, it splits into 3 different intervals. So you have to split it like that, 1 by 4 k dx plus integral 1 by 4 to 3 by 4 2k dx plus integral 3 by 4 to 1 3k dx. So this is something you can do, right? This function f of x, if you write 0 to 1, you have to write 0 to 1 by 4 f of x dx plus 0, 1 by 4 to 3 by 4 f of x dx, 3 by 4 to 1 by 3 by 4 to 1 f of x dx. Now f of x from 0 to 1 by 4 is k, 1 by 4 to 3 by 4 is 2k, 3 by 4 to 1 is 3k. Okay. Now remember, k is a constant. Okay, so you just have to multiply by x, and then x takes values 1 by 4 to 0. So this is just 1 by 4k plus, this is half, right? So 2k times half plus 3k times 1 by 4 has to be equal to 1. You can solve for k. So let me see. K by 4 plus 3k by 4 is k. There's another k. So you get k equals 1 by 2. Okay. I hope that's correct. It's k plus k, 2k, k is half. Okay. So you just solve for k. So this is also a typical example. So this got to help you identify which is a valid PDF. So one value of k gives you a valid PDF here. Okay. So once again, if you look at this problem, for instance, where does which is the, you know, if you fix a small epsilon interval, which is the area where it takes higher probability? It's between 3 by 4 to 1, isn't it? That's the place with the maximum PDF. You can draw the CDF corresponding to this. It will be continuous. It will be very sort of straight line, 3 straight lines leading up to 1. Okay. Alright, so this is the definition of the density function. Once again, the density function is probability, sort of probability per unit length. For small lengths, it can vary over the length itself. So you have to integrate to find the actual probability. That's very important. PDF is the derivative of the CDF. That's a good way to remember it. That's how you find the PDF. You can go back and forth by doing the differentiation and integration. Okay. So thank you very much. In the next lecture, we'll start looking at common distributions and common continuous distribution, look at the PDF, CDF, etc. Thank you.